Let's talk about common gate amplifiers. In this video, we're going to derive a complete expression for the gain, and we're going to work a couple of examples. Let's go ahead and get started. This is an example of a common gate amplifier. I can see that the gate is common because it's basically attached to the ground through a large capacitor. Since it's attached to a ground, and another word for ground is common, we call it a common gate amplifier. The signal is fed here into the source, and the load resistor is attached to the drain. Both of these capacitors are large. First of all, let's decide whether or not this configuration is inverting or non-inverting. We'll start off by assuming that the transistor has been properly biased into the saturation region. That means that the transistor is on, it's not in cutoff, and it's not in the linear region. Current is basically flowing downwards from top to bottom through that transistor. Let's call this voltage here VSRC, and I'm using VSRC to distinguish it from the signal voltage over here. Our signal voltage is going to be an AC voltage that rises and falls. It might be attenuated a little bit when it goes across this capacitor, but in any case, it's going to add to or subtract from the DC source voltage. Let's consider what happens when the signal voltage increases. I'm talking now about this part of the curve and this part of the curve. Well, if the signal goes up, then I expect the source voltage to go up too. That should cause the current going through this resistor, I sub D, to increase as well. I'm labeling it I sub D because D stands for drain, so I'm kind of assuming that the source current equals the drain current. That's a very reasonable assumption with MOSFETs because the gate is pretty much isolated from both the source and the drain. Because ID equals V source divided by R source, the drain current should increase here as well. That drain current passes through the drain resistor R sub D, and it will have an effect on the drain voltage, which I'll label V sub D. V sub D is going to be some voltage below our power supply, and I can just apply Ohm's law across the drain resistor R sub D. We've already noted that the drain current is going to increase when our signal increases, and I can see where it is in this equation. If the drain current goes up, then because of this negative sign, the drain voltage should go down. If I label our load voltage over here, I can see that the load voltage is just the AC component of our drain voltage. If the drain voltage goes down, then the load voltage should decrease as well. Since the load voltage went down when the signal voltage went up, I might conclude that this configuration is an inverting configuration. But that conclusion would be wrong, and in fact there's a problem with the derivation that I've just carried out. Pause the video and see if you can identify the flaw in the derivation. The flaw in the derivation comes when I identified this drain current and this drain current as the same. Let's label it in the circuit diagram. Is this drain current really the same as this drain current? No, it's not. It's not because we have some AC components of the drain current going out to the load resistor, and we have another component of the drain current entering from the signal. Because we have an AC component that actually determines whether the configuration is inverting or non-inverting, those portions of the drain current actually matter here. Let's see how they matter. And so that we don't get confused, I'm going to just draw a line through the incorrect part of our derivation. Let's temporarily remove our markings for the drain current from the circuit diagram. It's certainly true that when the signal voltage increases, that the voltage here at the source will also increase. They're connected by a simple resistor and a large capacitor. They move in sync with one another. Because of Ohm's law, it's certainly correct that the current through that source resistor will also increase. If the voltage went up, the current has to go up as well. I want to label it here I little d this time. We can still conclude that when the signal voltage increases, I little d should also increase. The question, though, is where did the extra required current originate? Did it originate up here from our power supply, or did it originate from our signal? The answer is that it actually originated from our signal, and that's what went wrong with the previous derivation. To get some sense of why that's the case, I want to add one more label to our circuit diagram. That's the voltage between the gate and the source. I'm going to call that VGS. In this case, the gate is grounded, so if we're talking only about the AC signal, we can see that the gate source voltage is going to grow and shrink depending upon the input voltage. This graph typically shows what a transistor will behave like. Notice that when you increase the gate source voltage, you typically increase the drain current. When you decrease the gate source voltage, the drain current will decrease until you get to threshold. When the gate source voltage is below threshold, the transistor turns off and you're no longer in the saturation region. Let's assume that we're operating at some DC point that's in saturation. So we have our particular gate source voltage and we have a particular drain current that's flowing. That drain current here would be the drain current through the transistor itself, and I'll label that I big D. What happens now when the gate source voltage is changed by the signal voltage? Well, we can see right here in our circuit that when the signal voltage increases, our gate source voltage actually decreases. It shrinks a little bit, doesn't it? Because the gate is connected to an AC ground. Let's now consider what happens when we apply our signal. When our signal increases, our gate source voltage actually decreases. On the other hand, we move up this curve when our signal voltage decreases. Since these up and down movements of the gate source voltage show up as changes in the drain current, the transistor can function as an amplifier. In fact, this ratio of the change in drain current to the change in the gate source voltage is called the transconductance. So this really represents the amplification action of the transistor. What conclusion now can we draw from this up and down movement of the curve? We see that when our signal voltage increases, then the drain current actually decreases. Going back over here, we can keep track of things. When I little d increases, it corresponds to a situation where I big D decreases. From the Kirchhoff current law at this particular node, it means that all of the extra current needed to raise the source voltage when the signal voltage goes up has to come from the signal, not from the DC power supply. If I label it I sub S, it means that I sub S also has to increase. Now let's think about what happens when the drain current, that is to say the actual drain current going through the drain of the transistor, decreases. If this current decreases, then it's going to cause the drain voltage to rise a little bit. If the drain voltage rises, then the load voltage will also rise. Now we've reached the correct conclusion. The common gate configuration is a non-inverting configuration. Let's now derive a complete expression for the gain of a common gate amplifier, and you'll see for yourself that it's non-inverting. We're going to start off by assuming that the transistor is properly biased in the saturation region. That's what we want. Our expression for the gain wouldn't be accurate if the transistor is cut off or in the linear region, for example. Current has to be flowing from high to low, and the gate has to have a proper DC bias point so that the transistor behaves like we expect. We'll assume that those conditions are met here from the start. We're going to need a small signal model for the MOSFET. In other words, I want to replace the MOSFET with some equivalent circuit that's more easy to analyze. It has 3 connections at the gate, the drain, and the source. Here's how we're going to model it. We'll assume that the MOSFET itself has an infinite input impedance. Since the gate's electrically isolated from the source and the drain, the leakage current, or the parasitic leakage, is usually really small. So this is a very realistic assumption to make. The MOSFET functions like a dependent current source, where the current flowing depends on the voltage applied at the gate. Let's label the voltage applied at the gate as VGS, the gate source voltage. Then the amount of current that the MOSFET is going to supply from the drain to the source is just given by GM VGS. GM is the transconductance, so it's a value that you would have to get in principle from the data sheet for a particular MOSFET. You can kind of get a sense that for small changes in the gate voltage, the amount of changes you would have in the drain current depend on that GM. So a transistor with a larger transconductance would usually give you a larger gain. What I'm now going to do is to redraw our circuit using our small signal model. Since the gate here leads to an AC ground, I don't really have to do too much on the gate side of the circuit. I only need to draw the right-hand part of the circuit. Let's start with our signal. An AC signal will see this signal resistance, R sub S. But if we have a large capacitor here, then the AC signal should pass right through it. So we won't include this in our equivalent circuit. Now we have the source resistor, our source, and then we reach the source of the MOSFET. So at this point, I'm going to draw the AC equivalent circuit for the MOSFET itself. So we have a current source right here, flowing downwards, and the current supplied is GM times VGS. Up here at the drain of our MOSFET, we have a drain resistor, R sub D, and it's connected to the power supply, which is just an AC ground. It's an AC circuit, so I'm drawing it as an AC ground. We also have our load resistor attached to an AC ground as well. It's a pretty simple circuit to analyze. Let's label our load voltage, V sub L, and our source voltage, V source. The first thing I want to do is apply the Kirchhoff current law at this node. We have two currents coming into the node and one current leaving the node. The current leaving the node is given by our current source, GM times VGS, and the currents coming into the node are going to be VL over RL from our load resistor and something similar for our drain resistor. The reason why it's negative is because if you stare at this resistor, you'll realize that the current, in a sense, is going the wrong way through that resistor. Current would normally go downwards from a high voltage to a low voltage. Because the current's going upwards from ground, we have to put a negative sign there. Let's simplify this just a little bit. VGS is just my gate voltage minus my source voltage. And then if you notice where the two resistors are in the denominator, we can also rewrite this here on the right-hand side as RL in parallel with RD. Our gate voltage is grounded through this capacitor, so it's an AC ground. We're then left with just GM times minus V source here on the left. The minus signs are going to cancel, and we're basically left with an expression that relates the load voltage to the source voltage. Let's do something similar at the bottom node. I'm going to apply the Kirchhoff current law down there as well. We have current coming into the node, and we have two currents flowing out of the node. Let's do the two currents flowing out of the node first. So we have the current going through the source resistor. That's this lower one. Now we have the current going right through resistor R sub S, so we need to apply Ohm's law. There's the voltage drop across it, and there's the resistance. And those two currents have to be equal to the current entering the node, which is just given by our current source. As on the left, we know that our gate source voltage is just minus V source. And what I'm now going to do is to factor out V source and group all of the terms. So here on the left, we have 1 over R source. Then we have one term from this expression right here, 1 over R signal. And then on the right, we have minus GM, and I move it to the left. so it becomes a plus. And then we're left with just one term, and I'm going to move it over to the right side of the equation. Signal voltage over the signal resistance. So all I've done is just rearrange terms here. Let's find V source over V signal. All we need to do here is just divide. What I want to do now is to just swap these two terms in the denominator. That can be done very easily by just changing the labels here. Let's now take a look at this term in particular. If we think about Gm as being the inverse of some resistance, then these two expressions are just 1 divided by R source in parallel with 1 over Gm. What I now want to do is multiply every term in this fraction by R sub s and by this fraction R source in parallel with 1 over Gm. For the numerator, Rs is going to cancel, so we're left just with R source in parallel with 1 over Gm. We'll have the same term here in the denominator, and then for this term, we'll be left with Rs. If you stare at this expression, it kind of looks like a voltage divider. In fact, we are going to have a voltage divider when we redraw our equivalent circuit. Looking at these equations, we can come up with something that's a little bit more comfortable to work with in the future. Let's combine everything that we've done to get an expression for the gain. The overall gain will just be the load voltage with respect to the signal voltage. We have two expressions that we've come up with. One relates the source voltage to the signal voltage, and then one relates the load voltage to the source voltage. Let's substitute in our expressions and see what we've come up with. There's the first term, and here's the second term. There's a small change I want to make to this expression. I want to move the transconductance Gm down to the denominator. Watch what happens when I do that. The first expression looks like an input voltage divider, and the second expression looks like a gain expression. It's a ratio of two resistances. It's all of the resistances attached to the drain divided by some resistance associated with the transistor itself. It ought to remind you of the common base configuration. This would have been little Re had we been working with bipolar transistor. So let's go ahead and just imagine that there's a little resistance right here in the transistor. I don't want to call it R little e like I did with the bipolar transistors. Let's instead just label that resistance as 1 over Gm. I like to do that because it creates a close analogy between the bipolar transistors and the MOSFETs. On the right-hand side, I can also separate these two resistors in parallel. This right expression can be split into two expressions. You see, here are the two resistors in parallel. Dividing it like this, though, gives us three distinct stages in our expression for the gain: an input voltage divider, a gain segment, and an output voltage divider. We can then see that the gain of a common gate amplifier can be thought of as the resistance looking up in this direction down here in the denominator, and the resistance looking up here in the numerator. That's why we have Rd here and 1 over Gm down here. The output impedance to the circuit is just R sub D, and you can see then where the output voltage divider will come from. Let's draw a more manageable small signal circuit for future reference. By inspection from the original circuit and going left to right, we have a signal voltage V sub S. We then have a signal resistance R sub S. We then have a source resistance R sub source. We now have a little resistance 1 over Gm, and that's it for the source side. You'll see that our input voltage divider matches our little diagram right here just nicely. We can then treat the transistor as a voltage amplifier. The gain will be given by this expression right here, positive Rd divided by 1 over Gm. So you can think of it as two resistances, the resistance up here divided by the resistance there. Finally, we have our output impedance, RD, and our load. This is the equivalent circuit that I'll use when we work the next examples. I really like this one because there's only one thing that you have to remember that's not so easy to do by inspection. All you have to remember is that the gain part of the expression of the overall gain for a common gate amplifier is given by resistor RD divided by 1 over Gm, where Gm is the transconductance of the transistor. Let's work an example together and try to find the gain. We're given the threshold voltage of the transistor and the transconductance. One thing to keep in mind is that the transconductance typically depends on the DC drain current. So if you're going to use the datasheet to look up the transconductance, you're going to have to know roughly where you have the transistor bias to start with. Let's start off here with a DC analysis to make sure that the transistor is properly biased in saturation region. We have a 12-volt power supply and 200 kilo-ohm resistors. Just by inspection, we can see that the DC gate voltage is going to be 6 volts. I can also see that the AC gate voltage is just going to be 0 all the time because it's connected to ground through this large capacitor here. Let's label it V sub G, and I'm now going to label this V source. And let's find the DC source voltage. We're going to be subtracting our threshold voltage, which was given in the problem. We therefore expect our source DC voltage to be roughly 3.9 volts. We can now find our DC drain current, which is just our source voltage divided by 39 ohms. It works out to 100 milliamps, which should also be passing from the 12-volt power supply to the drain. This means that the drain voltage is going to be some voltage lower than 12, and I just need to use Ohm's law across this 50 ohm resistor to find it. It works out to 7 volts. So if we have 7 volts here at our drain, 6 volts here at our gate, and 3.9 volts down here at our source, I can see that the transistor is not in cutoff and it's not in the linear mode. So it looks good. The transistor's properly biased in the saturation region, and now we can move on to the AC analysis. In this problem, we're given the transconductance, but in general, we would have to use our DC drain current to extract the transconductance from the transistor's datasheet. Sometimes these aren't very accurate, by the way. Let's clean up our circuit diagram a little bit, and I'm going to draw in a small resistor that's related to the transconductance. We'll label it here 1 over Gm, and I can think of it as the resistance inside the transistor. 1 divided by 0.2 makes 5 ohms, so it's a pretty small resistance. Let's proceed with an AC equivalent circuit. And I'm going to unwind it because I like signals to go from left to right. We'll start with our signal voltage, V sub S right here, and an AC signal will then see a 10 ohm resistor, and then it arrives at this branch and sees a 39 ohm resistor going down to ground. Looking up into the transistor is another resistance of 5 ohms. We now have a gain segment, and this is something that we just have to remember for common gate transistors, but luckily it's nearly the same expression that we had for the common base configuration. We just need to take that resistance up there divided by this resistance down here. So we have 50 in the numerator and 5 in the denominator. We then have a voltage divider. Our output impedance is just 50 ohms. The transistor behaves kind of like a current source. So when you look down the drain of the MOSFET, you see a very high impedance. We're just left with 50. And then finally, we have a 50 ohm load resistor. Let's label this our load voltage, and from this circuit, we can extract a complete expression for the gain. So we're going to have 3 components here. We have an input voltage divider. So the voltage divider set up between the 10 ohm resistor and these 2 resistors in parallel shows a particular characteristic of the common gate configuration. and that is that the input impedance tends to be really small. From the perspective of our input signal, the input impedance lies to the left of this line. In my equivalent circuit, it lies to the right of this line. And you might recall that for an amplifier, we typically want the input impedance to be as large as possible, but that's not what we have here with the common gate configuration. This input impedance is small because it mostly depends on 1 divided by the transconductance. The larger your transconductance, the smaller the input impedance. That can be advantageous if you somehow have a very low impedance source and you want to match it to the amplifier. But in general, this is not the kind of amplifier that you want to use. And in fact, common gate amplifiers really aren't all that common simply because the input impedance tends to be very small. The next term in our expression is the gain segment, which here is 10. Finally, we have an output voltage divider, which is just 50 over 100. Substituting in numbers here, we have a very modest input voltage divider, and we're losing about half our signal here at the output. Overall, the gain is 1.5. I simulated it with a 2N7002 MOSFET, and LT-Spice told me that the gain was 1.36. So it's not too far off from our pen and paper derivation here. Of course, there's some uncertainty associated with these transconductances, and that's probably where most of the error is coming from. Common gate amplifiers have a lot in common with common base amplifiers, but I suppose one of the easier things when it comes to the analysis is that you never have to worry about impedance reflection. Let's work another example, and you might notice here that our transistor is going to have a lower value for the transconductance. Let's start off with a DC analysis to make sure that this transistor is properly biased in the saturation region. Let's find our gate voltage, and we typically don't have much leakage into that gate, so we don't have to worry about the gate current being negligible the same way we would have to worry about the base current being negligible or not in a bipolar transistor. That means we can use large resistors in general when we're biasing the gate of a MOSFET. We have a simple voltage divider here. It's just our power supply times the fraction set up by these large resistors. The ratio gives us 6 volts. Let's now find our source voltage, and it's going to be somewhat lower than our gate voltage. We can see that the threshold here is 2.1 volts, and this gives us a reasonably good estimation of the actual source voltage. Give or take a little bit of voltage there, but it's a reasonable estimate. We have the DC value for the source voltage, and I can now find the DC drain current. It's just the source voltage divided by 500, so we wind up with 7.8 milliamps. You might notice that the drain current here is less than the drain current was in the previous example, and that probably explains why the transconductance is lower. Let's go ahead and find the drain voltage. So the drain voltage is going to be somewhat lower than our power supply, and I just need to apply Ohm's law to that 500 ohm resistor up here. When we plug in 7.8 milliamps, we wind up with 6.1 volts. So our drain voltage is higher than our gate voltage, and our gate voltage is at least a threshold higher than our source voltage. High, medium, and low. So the transistor is properly biased in the saturation region, and we can now move on to the AC analysis. Let's clean up our circuit diagram a little bit and draw our AC equivalent circuit. Let's draw it from left to right and follow the signal's path through the circuit. So the signal starts here, and it sees first a 50 ohm resistance. We'll assume it goes right through that capacitor, so of course the capacitor has to be sized appropriately as to not unwittingly make a high-pass filter there with it. At this point, we have 2 resistances. We have a 500 ohm resistance looking down, and we have a little resistance looking up, given by 1 over our transconductance. If I take 1 and divide it by our transconductance, I'll wind up with 50 ohms. Lower transconductance, a higher effective resistance. We can add that resistance to our equivalent circuit and move on to the gain segment. The higher transconductance is going to lower our gain a little bit, I have 500 ohms here in the numerator of the expression, and looking up from this point in the circuit, I have 50 ohms in the denominator. A higher transconductance typically leads to a higher gain. Since here we had a lower transconductance, our gain ends up getting divided by a larger effective resistance than it did in example 1. We've now reached the output segment of our circuit, and I can see that the output impedance here is just 500 ohms in parallel with something very large looking down the drain of that MOSFET. So we'll just estimate that it's 500. And then finally we get to the load. Our load resistance here is just 500. I'll label our load voltage, and using this simple circuit, we can come up with an expression for the overall gain. So we start off here with a voltage divider. We have two resistors in parallel, and they're dividing over that 50 ohm signal impedance. We then have a gain segment, 500 over 50, and then we have an output voltage divider. If you've been following along in all of my videos, I hope you've recognized that I've tried to do this in a very consistent way from transistor to transistor. And this is really a good way to remember it. You're almost always going to have an input voltage divider, some kind of expression for the gain due to the transistor itself, and then some output voltage divider. In this case, we have a modest voltage divider at the input. We have some gain due to the transistor, and then we have some modest attenuation at the output side. Something that you might notice when you're looking at the common gate amplifiers and comparing them to, say, the common base amplifiers is that this middle number tends to be larger for bipolar transistors than for MOSFETs. And that's related to the fact that this little Re, or the emitter resistance of a bipolar transistor, tends to be smaller than this effective resistance, or 1 divided by Gm, that we're seeing here with MOSFETs. And that's really typical. You tend to get larger gains from common base amplifiers than with common gate amplifiers. When we multiply these three numbers together, we wind up with 2.38 as the overall voltage gain. That's not very good, but it's not very bad either. I simulated that with a 2N7002 MOSFET on LT Spice, and the simulator told me that the gain ought to be about 3.43. We're within a ballpark. I think the most reasonable explanation for why these two gains are a little bit different is probably just because my value for the transconductance, I used here 20 millisiemens, probably doesn't match the simulator's value for the transconductance. If we were to actually build the circuit, I expect that we would see some difference in the actual gain from what both me and the simulator is giving for the gain. We're certainly fairly accurate here, though, in our expression for the gain. That wraps it up for the common gate configuration of the N-channel MOSFET.